You know, when you flip a switch, the lights just come on. It feels so simple, right? But behind that one simple act, there's this massive, continent-spanning machine that has to perform a perfect balancing act. And it has to do it every single millisecond. Today, we're going to talk about what happens when that balance fails and a ticking clock starts somewhere you can't see.
Because, it's not some slow, graceful decline. No way. It's a frantic, automated battle against the laws of physics that unfolds faster than you can even blink. This is really the story of those few seconds that stand between a stable, happy power grid and a total, catastrophic collapse. So, okay, let's dive right into this race against time. The whole heart of the issue, really, is this constant, invisible struggle to keep the grid in perfect equilibrium. The power we're all generating has to match the power we're all using, moment to moment.
Now, before we get into all the ways things can go wrong, and believe me, they can, it's worth taking a second just to appreciate the miracle that actually works flawlessly billions of times a day. We're talking about the grid's perfect balance. It's like the invisible heartbeat that powers our entire modern world. So here's the fundamental challenge, the thing that makes this so hard. Unlike, say, water in a reservoir, you can't really store huge amounts of electricity efficiently. It's just not practical. So the power you're using to watch this right now, it was literally generated just a moment ago. This means that supply has to perfectly match demand, in real time, all the time, no exceptions. So how do grid operators even know if things are in balance? Well, they watch one number above all others, the frequency. In North America, it's 60 hertz. In many other places, 50 hertz. The best way to think about it is like a heartbeat. A steady, solid 60 hertz means everything's in perfect harmony. But if that number starts to wiggle, even a little bit, that's a huge sign of trouble. And check this out. This diagram shows you just how critical that frequency is. Think of power system stability as a three-legged stool. You've got voltage, that's kind of like the pressure in the system. You've got rotor angle, which is all about making sure the generators are spinning in perfect sync. And right there, holding it all together, is frequency stability. If any one of those legs starts to wobble, the whole system is at risk of just falling right over. Okay, so what actually happens when that delicate balance is broken? Well, that's what we're talking about next. This is where a tiny disruption can escalate into a critical, system-wide emergency, and where that clock really starts ticking. So the technical term for this is underfrequency, and it's a really simple concept with absolutely massive implications. If the frequency drops from 60 hertz to, say, 59.5, that is a clear, unambiguous signal that we are using more power than we are making. The grid is being overdrawn, and every single generator connected to it immediately starts to slow down. So what could cause something like this? Well, it's usually something sudden and big. Think about a massive factory firing up all of its heavy machinery at the exact same time, or a huge power plant suddenly tripping offline for some reason. Even a critical transmission line failing can instantly throw the entire grid completely out of balance. And what's really fascinating here is that having too much power over frequency is actually not nearly as dangerous. With too much power, an operator can just call a power plant and say, hey, dial it back a bit. But with underfrequency, the problem is a lack of power. You can't just conjure a brand new power plant out of thin air in a few seconds. That leaves the operator with terrifyingly few options, which is what makes it so critical. And that lack of options is what turns this whole situation into a genuine race against catastrophe. The dangers of this slowdown aren't just, theoretical. They are physical, they are mechanical, and they threaten to literally destroy the very equipment that powers our entire lives. I just love this quote. It's so blunt, It's from an engineer explaining what happens when you run equipment at the wrong frequency. It's not just that it's inefficient, it's actively destructive. Death threatens. He's talking about the death of the equipment, and yeah, potentially the death of the entire grid. So let's break down why it's so dangerous. First off, you've got these massive turbines in power plants, right? They are precision engineered to spin at an exact speed. If you slow them down, you introduce these immense mechanical stresses that cause fatigue and cracks. Second, the cooling systems, also designed for 60 hertz, become way less effective, which leads to overheating and even fires. And finally, and this is the real kicker, the generators themselves have self-preservation systems. If the frequency gets too low, they will automatically shut down and disconnect from the grid, just to save themselves. And that instinct for self-preservation, well, that's exactly what can trigger a system-wide disaster. It creates this terrifyingly fast, vicious cycle. Here's how it goes down. Demand is higher than supply, so the frequency drops. A generator's protection system screams, "This is dangerous," and trips itself offline. But now there's even less supply for the same amount of demand, so the frequency drops even faster, and that causes the next generator to trip, and then the next, and the next, in this terrifying cascading failure that can bring down an entire grid in just a matter of seconds. So, how on earth do we stop this catastrophic domino effect? Well, thankfully, we have engineered this incredible high-speed safety net. These are the automated lines of defense, all designed to catch the grid right before it falls. And the key word here you got to remember is automated. There's no time for a human being to sit there, look at the data, and decide what to do. These protection systems are built right into the fabric of the grid itself, and they operate in milliseconds to stop that vicious cycle before it can really get going. Okay, here's a really specific example of how that works. This is a two-stage protection system. Let's say we're on a 50 Hz system. If the frequency drops to 48.5, an automated command is instantly sent to a grid circuit breaker. But if that's not enough, and it falls even further to 47.5, a much more drastic command is sent to trip the main generator breaker itself. It's a calculated, staged response to a crisis that's getting worse by the millisecond. Now, beyond just tripping things offline, we have even more sophisticated tools. The most famous one is probably load shedding, which is what we all experience as rolling blackouts. It's a tough pill to swallow, but it's an automated system that intentionally cuts power to some areas to reduce demand and save the rest of the grid. But we also have things like governor controls on turbines for instant speed adjustments, massive battery systems that can inject power in a fraction of a second, and even programs that pay huge companies to cut their power use during an emergency. And, this incredible engineering has kept our grid remarkably stable for decades. But that grid was built on a foundation of predictable, spinning machines. Now, as we shift toward cleaner energy, the very physics of the grid is changing, and it's forcing us into a whole new kind of balancing act. The move to renewable energy is absolutely essential for our planet, no question. But it introduces a really fundamental challenge to the physics of how the grid works. Wind and solar power, well, they're just different from traditional power plants, and that difference directly impacts frequency stability. And here's why. Traditional power plants use these massive, heavy spinning turbines. The sheer physical momentum of all that spinning metal creates something called system inertia. Think of it as the grid's natural built-in resistance to change. It acts like a giant shock absorber. While wind and solar are connected to the grid through electronics, they don't have that big, heavy spinning mass. So as we replace spinning turbines with solar panels, the grid loses its natural shock absorber. In fact, some studies are projecting a 70% reduction in this inertia in just a 20-year span. That means when a disturbance does happen, the frequency is going to drop much, much faster than ever before. And that, right there, brings us to the final, crucial question. All those safety nets we built, they were designed for the old, high-inertia grid. So, as we build a cleaner, but fundamentally less stable grid, are our automated defenses going to be fast enough and smart enough to keep up? That is the new race against time. Something to think about the next time you flip that switch.